Hello everyone, my name is Olivia Mawalim. On behalf of our team from Japan Advanced Institute of Science and Technology, I would like to present our work entitled Speaker Anonymization by Bit Shifting based on timescale modification. This presentation contains of 5 main parts, including introduction, speaker anonymization, proposed method, experiments, and finally conclusion and future work. Before I explain our work in detail, I would like to introduce why the voice privacy preservation technology is important. Exposing speech information causes social problem as shown in the news collection in this slide. Current speech technology using AI was reported can clone our voice, for example in the purposes of mimicking actors or for cyber criminals. AI speech synthesis is quick, easy, and uncannily good. Another news also shows that new AI research makes it easier to fake someone speaking. With this advanced technology, the criminal can pretend to be a family of a victim and demand a big amount of money or even other mischievous purposes. So, the effort for developing a speaker anonymization system is proposed as a solution to suppress and conceal speaker identity of speech in the voice privacy challenge. The general framework of a speaker anonymization system is shown as in this figure. There are 4 main requirements for a speaker anonymization system. First, the speaker identity must be hidden. Second, the output anonymized speech should be natural and intelligible. Third, language information should be preserved. And lastly, it follows a speaker-to-speaker correspondence. In other words, each speaker corresponds to one pseudo-speaker. The scenario of speaker anonymization based on voice privacy challenges are as follows. And there is a possibility attacks could happen or defined when the attacker has access to various amounts of data with certain conditions. The evaluation of speaker anonymization will be explained later in this slide. In addition to the definition and protocols, there are 2 categories of baseline systems introduced in the voice privacy challenge. The primary baseline is based on neural source filter model or NSF model and X-factor speaker embedding, so-called machine learning approach. Meanwhile, the secondary baseline utilized the McAdam coefficient for manipulating the speaker identity, so-called signal processing approach. The variation of the primary baseline is depending on the machine learning model, while the secondary baseline is depending on the coefficient range. This block diagram shows our proposed methods based on timescale modification or TSM. We investigate pitch shifting by resampling using 2 major categories of TSM algorithms for speaker anonymization, including SOLA and PVTSM. Unlike a vocoder, this approach synthesizes bits via frame relocation and adaptation. However, while TSM can synthesize higher quality voices than a conventional vocoder, it cannot be used to analyze pitch and timbre independently. The figures in this slide indicate the sample of output after pitch shifting using TSM algorithms by 2 semitones. First row shows waveform. Second row shows chromogram of speech signals. Third row shows F0 trajectory in Hertz, extracted by P-Yin algorithm. Mathematically, the pitch shifting procedure is expressed by this equation, where n is the shift parameter in semitone. A semitone or half step is a commonly used musical interval representing different pitches between neighboring notes on the piano. 1 semitone is equivalent to 100 cents. For experiment, 2 datasets that divided into development and evaluation subsets were used, including LibriSpeech and VCTK. 2 types of metrics are considered for evaluation. First, privacy metric, which is evaluated by using an ASV system. Second, utility metric, which is evaluated by using an ASR system, pitch correlation, and the gain of voice distinctiveness. The ASVeval scenario in VoicePrivacy Challenge 2020 is as shown in this slide. 3 cases are considered, including original enrollment, original trials, or as called as OO case, and then original enrollment anonymized trials, or OA case, and both enrollment and trials utterances from anonymized bits, or AA case. A better privacy is defined when the system could output higher equal error rate, or EER. Next, ASVeval is used for evaluating the primary utility metric in terms of speech intelligibility in word error rate, or WER. A lower WER means a better quality of anonymization. These figures plot the mean results of the overall performance of our proposed methods and the baselines. In both cases, anonymization using TDIF-SOLA algorithm failed to preserve the privacy in terms of the EER. On the other hand, methods based on the PV-TSM algorithm could achieve higher privacy and utility than the secondary baselines in all cases. Even it could achieve highest privacy in AA case or lazy informed case. Next, considering semi-informed attack model as described in the VoicePrivacy Challenge 2022, the attacker has access to the anonymization method for the utterance level without knowing the detailed parameters that represent the speaker identity. The results of this evaluation are as follows. The proposed methods based on the PV-TSM could achieve comparable results to those of the primary baselines. Alternatively, we calculated the pitch correlation and the gain of voice distinctiveness. The results show that the proposed method could achieve best results, highest pitch correlation, and lowest gain of voice distinctiveness in comparison with the baselines. To conclude, we have investigated two major TSM algorithms, TDIP-SOLA and PV-TSM, for speaker anonymization. TDIP-SOLA algorithm can be used for pitch shifting but is insufficient for privacy protection in the ASV system. In contrast, pitch shifting by the PV-TSM algorithm for speaker anonymization providing the highest balance of privacy utility metrics, especially in lazy informed scenario. Method of PV-TSM also can preserve secondary utility metrics, including pitch correlation that can represent intonation and the gain of voice distinctiveness to some extent. In future, we will investigate more the shift parameter and nonlinear pitch shifting using the PV-TSM algorithm. This is all my presentation. Thank you.